This conference will now be recorded.
So very good evening, students. Today we will be continuing discussions on various numerical problems on the chapter first and second electrostatics. So where we will be discussing electric charges, like problems, numerical problems related to electric charges, electric field, potential, capacitance, capacitor, etc. So these questions which we are going to solve are all from the previous JEE main papers, so which are really very important, and some of them are really tricky to understand sometimes. So we'll solve and try to understand all of them. So let's start today's class. So in this first question, it is said that a long cylindrical cell carries positive surface charge sigma in the upper half and negative surface charge minus sigma in the lower half. As you can see in the figures, upper half, lower half, upper half, lower half, like that. So upper half is positively charged, lower half is negatively charged. So the question is, the electric field lines around the cylinder will look like figure given in. So mainly the question is the pattern. What will be the pattern of the electric field lines in this case? So the first one, let us discuss. So suppose this is a cylindrical cell which has, like you can see, actually top view of the or cross sectional view. You are seeing the cross sectional view of the cell, cylindrical cell. You have something like this, okay, but you are looking from this side, so you just see this portion alone. So this is upper half, suppose this is positive and negative is this half. You have to tell me which pattern of the electric field lines will be the correct. So we know electric field lines always emits from positive charges and it goes to infinity if there is no negative charge around. Okay, it goes to infinity. But if suppose there are positive charge and negative charge nearby, then what happens? The electric field lines will start from positive and it will end at the negative. So like that it will be like this. Okay, so this is the situation. So in this you have to see the first one. See, the field lines are electric field lines are emitting from positive, okay, and they are actually going infinity. You can see that they are not going immediately and meeting over here. So we cannot say this pattern is perfectly correct, even though the field lines are entering at the negative charges and emitting from the positive charges. Actually, this field line seems to come from infinity or from somewhere else. Okay, and these field lines which are emitting from positive charges, they are going somewhere else instead of meeting at this particular position. Okay, so this is not that correct. Okay, this here there is actually no sign of, see, the same problem. Actually electric field lines, these lines must go and meet here. Okay, but they don't have sign to go and meet at the negative point. So this also has the same problem. Let us see this case. So this case, you can see the field lines are coming and ending. This is something like this is ending here, and then it is starting something is from here. Actually, the problem is, like, see, I have no breakage or discontinuity in the field lines. So field line should be continuous. That is another point. Field lines must be continuous. Must be continuous. But if you look here, there is a discontinuity. Discontinuity. So this is not going to satisfy. And rather, another problem in this case, you look here, the field lines are actually emitting from negative. So this is not true. This is not true. You can see others are fine, but these field lines are emitting from the negative charges. So this, which is not correct. Again, the continuity issue is also there. So field lines, even though they are not forming a closed loops, but still field lines will be continuous. See, the D, option D is actually most relevant in this case, or most appropriate, because the field lines are emitting or emanating from positive charges, and they are meeting at the negative charges, and there is no discontinuity. Okay, so in this way, and also see the negative charges, the field lines are entering here, and here it is emanating or emitting. So this is most appropriate answer for this question. So what is the answer? So this is the most appropriate pattern of the electric field lines for this uh, cylindrical cell, which has positive charges at the upper half and negative charges at the lower half. Okay, so now this is a problem from parallel plate capacitor. We can read this problem. The problem states that a parallel plate capacitor of capacitance 90 picofarad is connected to a battery 20 volt. I'm just trying to draw. Let me draw in the middle. So there is a parallel plate capacitor. You know, like in parallel plate capacitor, so upper plate has to be, or any of the plate has to be positively charged, and other plate has to be negatively charged, so it will act as a capacitor, parallel plate capacitor. And see, in between these two plates there could be air, or there could be some dielectric material. So initially the parallel plate capacitor has capacitance. We can write that as C0, which is 90 picofarad given, and this capacitor has been connected to a battery of 20 volt. Okay, if a dielectric material of dielectric constant 5 by 3, K is equal to 5 by 3. So now this was initial case, and now the space between the plates is filled with a dielectric material having dielectric constant 5 by 3. Okay, now the question is, the magnitude of the induced charge will be what out of these four? Therefore you have to find out the induced charge. Suppose initially when the dielectric material was not there, the charge was plus q on this plate and minus q on this plate. Now there is a induction due to this dielectric material. As you know, if you induce, like if you insert a dielectric material, and if you apply, like if you connect this plate with a battery of 20 volt, then there must be some charge induced in the both plates. So what is that induced charge? So this dq is the induced charge. You have to find out that. So how to find out induced charge? So look here, what we can do. We know when the air was there, what is the capacitance? Now we can find out the charge, initial charge. So that is maybe Q0. So we can do C into V. That is C0 into V. V is 20 volt in this case. So 90 into 20 for 10 to the power minus picofarad means 12. This is suppose coulomb. This is coulomb. So this was then 18 10 to the power 10 to the power minus 10 coulomb. It was the initial charge. Now we have to find out the capacitance after inserting this dielectric material so that we can find out the final charge stored in this capacitor first. So capacitance after inserting the dielectric material can be obtained as K into C0. K means 5 by 3 and C0 is 90 picofarad. So this would give you 150 picofarad. Okay. So what will be the charge then? So we have got, I'm just directly writing over here. It is 150 picofarad. One 50 picofarad is the capacitance we have got. Now, what is the charge after insertion of dielectric material? That charge will be Q is equal to C into V. C is 150 picofarad into 20. This will be 10 to the power minus 12 coulomb. So we will be able to get here 30. I think you will get something like this. So this is 10 to the power minus 12 coulomb. If you simplify, we'll just keep up 10 to the power minus 10 itself. This is a coulomb. Now look, I can just find out the delta Q. Delta Q is Q minus Q0. So what is Q? Q is 30 into 10 to the power minus 10, and this is 18 into 10 to the power minus 10, and this is whole thing is coulomb. This is 12 into 10 to the power minus 10 coulomb. So we can write 1.2 10 to the power 9 coulomb. So this will give you 1.2 nano coulomb. Okay, nano coulomb. So you look, this B, option B will be the correct answer in this case. Okay, this is very simple, not very tough question, but still we have to keep patience and solve it step by step. Okay, so now let us go to the next question. So this is a very nice question. This is from electric field. So let us see what is the question. The 2-point charges Q1, which is given as square root of 10 microcoulomb, and Q2, which is minus 20 microcoulomb, are placed on the x-axis at x is equal to 1 meter and x is equal to 4 meter respectively. That means there are two charges Q1 and Q2. One is negative charge, another one is positive charge. They are placed on the x-axis at x is equal to 1 meter and x is equal to 4 meter respectively from the origin. Now you have to find out the electric field at any point 3 meter away from the origin along the y-axis. On the y-axis, where 1 by 4 pi epsilon naught, this constant you can take as 9 into 10 to the power 9 Newton meter square per coulomb square. Look, we have a schematic over here for the same problem. Let me just tell you. According to the question, the Q1 charge is at x is equal to 1 meter away on the x-axis from the origin, and Q2 is 4 meter away from the origin on the x-axis. Now you have to find out electric field at this point here. Look, this point here. This is 3 meter away from the origin on the y-axis. So what we know, electric field can be calculated using this formula, E is equal to Q by, if you know the charge due to which you can find out you are going to find out electric field at any point r, the formula will be Q by 4 pi epsilon naught into r square. Suppose you have a charge Q, point charge we are just considering, you are calculating electric field at any point here at distance r. So then this is the formula. So this is the formula to find out the electric field. Now you look here in the options. In the options you can see this actually, these are in the vector form. Okay, in the unit of volt per meter, in these are all in vector form. So you can see the electric field. If you want to calculate the electric field for individual charges, you'll be able to do. You need to know what is the r. Suppose I consider Q1. What is the r? Let us say this is r1. So this is the r1. This is the straight line distance between these 2 points. Okay. And for Q2, this is the distance, straight line distance. And Q2, see Q1 is a positive charge. So Q1 is a positive charge, and you know electric field will be always directed from positive to negative or less positive charges. So the direction of the electric field due to Q1 charge is away from the Q1, and that is this one. Okay, this is E1. Okay, so let me first calculate the electric field at this particular point, which is 3 meter away from the origin on the y-axis. So let me just write E1 as a magnitude. The magnitude is Q1 by 4 pi. Okay, so we'll just directly write this. What is Q1? Q1 is given as root over 10 microcoulomb. I am writing as coulomb, 10 to the power minus 6 coulomb, by 4 pi epsilon naught r square. Here it will be r1 square. What is r1? So if I just take this as a right angle triangle, so this is 3 unit, this is 1 unit. So this will give you 3 square plus 1 square. Okay, and 1 by 4 pi epsilon naught, you can take this as 9 into 10 to the power 9, and this as a whole will give you volt per meter. Okay, so what is the magnitude then? So this is 10, and this is square root of 10. So I can write, and here it is 9. So 9, let it be there, and this is 10 to the power minus 6. This is 10 to the power 9. So it will give you 10 to the power 3 divided by square root of 10. Okay, this is the magnitude of the electric field, but we have to write in terms of vector. So look, if I write in terms of vector, this electric field, since it is making an angle θ1 with this x-axis, I can see this is θ1, means if this is θ1, then this also I'm sorry, it is here. This must be also a theta 1. This will also be theta 1. So I can actually break the component of the electric field. See, if I want to write in terms of vector, what I have to write, E1 is equal to, I'll be just erasing this calculation part once I write this full, and let me let me write the magnitude here itself, E1, because I need more space. So 10, sorry, 9 into 10 to the power 3. I'm just keeping this square root of 10 down itself in the numerator itself, denominator itself. Let me just clean this portion, I may need it. So E1 I'll be writing in terms of vector. See, E1 vector, I have to see, this is U1, so it is making an angle theta with this negative x-axis. So it must be having a component here, E1 cos of theta 1, and along this direction E2 sine theta 2. Okay, so I can actually write this as E1 cos of theta minus I cap plus E1 sine theta 1 into j cap. So this will be the vector form of the electric field. Now I can just take this E1 as common from all of them, and I can write this as minus cos of theta 1 into I cap plus sine theta 1 j cap. But the question is now, what is theta cos theta 1 and what is cos theta 2? Sine theta, cos theta 1 and sine theta 1. That you have to put the value, then only it is. And also, anyway, you know the magnitude of the electric field, E1, we can write it here. Before that, let us just find out, see this figure. You can just think, what is tan theta 1 here from this triangle, this particular triangle? What is tan theta 1? So tan theta 1 will be perpendicular by base. So what is perpendicular in this case? See, this is angle, means this is perpendicular, this is base. So 3 by 1. So if this tan theta 1, I can write like this. See, from this notion, we can just draw a triangle like this where tan theta can be 3. So 3 is the perpendicular, this base is 1 in it. So tan theta will be, so this will be root tan theta. This is the hypotenuse, root over square root of tan theta, like square root of 10. Square root of 10 will be the hypotenuse in this case. So then we can find out cos theta 1. What is cos theta 1? That is base by hypotenuse. What is base? Base is 1 by hypotenuse, this. Similarly, we can find out what is sine theta 1. So this trick is very, very important and actually very, very useful. In many cases where you don't know a value of particular angle, you can actually find out in this way. So sine theta 1 is equal to perpendicular by hypotenuse. So these two values we can put it here and then write properly, putting the value of E also, E1 also. So let us put this value 9 into 10 to the power 3. Let me keep this by root 10. See, cos theta is minus 1 by square root of 10 I cap. And here this is 3 by square root of 10 j cap. Now look, I have square root down in the denominator in this factor. If I just multiply, what will be the, I'm just erasing here. Okay, so if we just multiply this inside, then I'm just going to keep this 9 into 10 to the power 3. This is obviously all are the volt per meter here. Okay, so this will give you minus I cap plus, let me do one thing, let me keep the factor out, 10 to the power 3 out, let me write this 9 minus 9 I cap 27 j cap into 10 to the power 10 to the power 3 volt per meter. So this is the vector form of electric field electric field produced at this particular point due to the charge q1. So what we can do, we can just write this down somewhere and then solve the, or let me write it here. What we have got, e1 vector as minus 9 I cap plus 27 j cap whole into 10 to the power 3 volt per meter. Okay, now I'll just erase this part and find out the electric field produced at the given point due to the charge q2. So as I said, q2 charge is minus 25 microcoulomb. So the electric field will be actually inward in the sense it will actually be directed towards the charge itself. So as you can see from the figure, so it is towards the q2 charge. But this is R2 now. So R2 will be actually, R2 square will be 3 unit square plus 4 unit square. So it will be 25. Okay. So we have got R square. Now we know E2 will be, Q2 means minus 25. Anyway, we are just trying to get magnitude. Then we'll take the component. So 25 into 10 to the minus 6 coulomb into 9 into 10 to the power 9 into 10 to the power 9 divided by R square. R square is 25 again. So it will be actually giving you 9 into 10 to the power 3 alone. Okay, so this will give you this much. So we can write the magnitude. Nine into 10 to the power 3 volt per meter. We have got the magnitude now. In a similar way, we'll try to write down the vector form of this electric field E2. So look here, electric field is directing this way and it is making an angle. If this R2 is making an angle theta 2 with the horizontal x-axis, then look, this angle also will be theta 2. So we can write, see, we can break this electric field into two components, one along this way, another along this way. So E2 cos of theta, it is along x cap, and this is E2 sine of theta 2. This is theta 2, sine of theta 2, which is along negative y axis. So we can write it. E2, let us take common because we are now a little bit experienced what we are going to write. So it is along cos of theta 2 into I cap minus sine theta 2 into j cap. Okay, so this is the thing. Now see, we can find out, see, from the whole triangle, this one, the bigger triangle, you can see from there we can write tan theta is equal to, in fact you can see, you know that, right? So in this case you can find out easily what is cos theta and sine theta. See, cos theta will be, so cos theta will be base by hypotenuse. So hypotenuse is here 5, and this is sine 2 theta will be perpendicular, that is 3 by hypotenuse. Okay, so hypotenuse is 5. So we can just write it here. So 9, let me write here once, 9 into 10 to the power 3, and here see I cap I'll keep as it is. So it is 4 by 5 I cap, and this is minus 3 by 5 3 by 5 j cap. Okay, in this way. All right, let us see what is going to happen. Okay, so we can now multiply. So this is 9 into this by 5 minus 3 by 5 into 9 j cap, and let me just do one thing because all of them are of the order of 10 to the power minus 2. Let me write here 90, here 90, let me write here 10 to the power 2. So the calculation will be easier. So this is actually 148. So this is 72 I cap, and this will be minus this into j cap. Okay, into 10 to the power 2 volt per meter. So this, in this case also, if we just multiply 10 here, I think there is some okay, let us do up to the end and then see what happens. 90 and this 27, three by 4 tan theta. So if I write 3 by 4, so it will be 5 alone. So yeah, we are so far all right, no issues. So now if we make it 10 to the power 2, it was 4 by 5, it is all right, this is also fine. 9 into 10 to the power 3, all right. Okay, so we'll just do one thing. Let us make it 10 to the power 2 itself, and let me do the addition of these two vectors. So let me write it here. What is E2? I'll write it here, and E1 also side by side, so that we can. Okay, so here it is 20, 32. It seems there are some problem. Okay, so what I'll do, I'll just keep it here itself. Let us not worry about the final calculation. Okay, and here also, in this case also, Okay, we have done a small mistake in this, actually, in the calculation of this. Actually, it will be, there will be 10 down. Okay, so here it is 10 and here it is 3 by 10, if I remember. Yes, so 3 by 10, and here let us keep this 9 into 10 to the power 3 as it is. Okay, now let us do the addition of the vectors. This is 2 and EU1, let me write it here. So 9 into 10 to the power 3, and here it is minus 1 by 10, and this is 3 by 10 here. So actually there, this 10 we had just forgotten, we just missed this 10, so that's why there was the problem. So now this you have to do vector addition to get the total electric field or resultant electric field at this point. In the vector form we can just see 9, let this be there out itself, common, both of them, this vector is there. So here it will be, so 4 by 5 minus 1 by 10. We have to do small calculation of LCM. So this is 3 by 10 minus 3 by 5 j cap. So if you do that, you'll see this is 8 minus 1, so 7 by 10 I cap, and this would give you plus 3 by 10 JQ, sorry, J cap, and along with that this 9 into 10 to the power 3 volt per meter. Okay, so this 10 I can just resolve here, and this 9 if I multiply inside, so what we will get finally, this will be 63 I cap. Okay, so 63 I cap. I hope it will be actually minus, this will be minus again, so minus 27 J cap. Okay, so this will be the answer finally. You can see this first option will be the correct answer for this case. So there was a little calculation mistakes in between, but the concept, I hope you have grasped the concept and the way we are doing. The space is less, that's why it is looking like very hazy, but anyway you have got the essence, I hope. So we'll move on to the next question. So previous one, since I was doing each step, so it took long time. So now this question is again another interesting question. So let us solve it. For a uniformly charged ring of radius, so when you have a uniformly charged ring, electric field on the axis has largest magnitude at a distance h from its center. So when you have such kind of ring having a radius r, it will produce some electric field, an electric field on the axis. Suppose this is the distance h. Okay, this is the distance h from the center of this ring. First of all, you need to know what is the electric field. Electric field in terms of r and h. Okay, so suppose it has charge q on it. So at any distance from this ring on its axis, what will be the electric field? So let us say we are finding out electric field at this point h due to this uniformly charged ring which has radius r and it has charge small q. So it is it will be actually obtained as QH divided by R square plus H square whole to the power 3 by 2 along with a constant quantity K. So this will be actually the electric field. Okay, constant quantity is actually 1 by 4 pi epsilon naught. This is K. Okay, so once you know the electric field, what is the question you have to answer here? They have already told that the electric field on the axis is maximum at h distance from the center. So what is the value of this h? You have to find out that. What is the value of h? So in such cases, whenever you see some quantity is maximum or minimum with respect to some variable, like suppose in this case with distance, at some distance it is maximum, then what you have to do, maximum or minimum at any point you have to check by taking derivative is equal to 0. Okay, this is the first thing you should do to check whether a particular quantity electric field over here is maximum or minimum at this particular point. Anyway, they have told you maximum, so it implies that dE by dH, the variation of electric field with respect to H will be 0. Okay, so if this is the case, then we can just take the derivative of this and then make it 0 so that you can get an equation to find out H. Okay, okay, let us just do it. See, this is the derivative. See, you have variable here, you have variable down also. That means it is it is kind of a function which is u by v. Suppose both of them are function of x. Okay, so u by v you have to do in that formula. So what is the formula? V of x whole square v of x into du dx minus u into dv dx. Okay, this is the formula for doing the derivative for u by v functions. Okay, so in this case we'll just use that form. Let me start from here so that we can finish it in short space. Okay, d e by dh is equal to, see, k and q, these are constant. I'm not so much bothering, let them be outside. So here, see, look, this is the v function, a square whole to the power 3 by 2 and whole square of that, so that will be cube. Now I have to, I'm just writing this e just a little bit up. E is equal to k qh by r square plus square whole to the power 3 by 2. Okay, so I'm just doing the derivative of this quantity. So this is square of this denominator, square of v, suppose, then you have to keep the v here and take the derivative of the u. So u will give you just 1, because dh by dh, okay, will give you 1 minus, you keep this h here and do the derivative of this particular term. So this will give you 3 by 2 into r square plus h square 3 by 2 minus 1, which will give you half of this, so to the power half, into, again this is h square, so it will give you 2h. Okay, so this is the derivative part. Anyway, I am just making this into 0, so I don't bother about this denominator, neither I bother about this. Okay, I'll just take care of this part alone. Okay, so the whole part is equal to 0. So let me just erase these things, because if you divide anything like 0 with anything or multiply with that, will make you 0. Okay, so here I'll take this r square. R square, it's a square whole into 3 by 2, and I'll take this way. So this will give you 3h square. Um, this is h square whole to the power half. Now I can just solve it. So there, here in this side, this is h square, and here it will be just h square plus r square plus h square. Okay, so this would give you 2h square is equal to r square. Hence, h will be r by square root of 2. Okay, so this is the value of h, where the maximum electric field will be obtained. So this h has to be r by root 2. Okay, so the answer is the first option. Okay, all right. Now, so the key point is that you should remember, because you cannot derive this all the way because time will be less. So you should remember, for a uniform ring, what will be the electric field, expression for the electric field. And whenever there is maximum or minimum word, you can just make this 0, this derivative 0, and just do the calculation quickly and you will get the answer. Let me now solve this one. So this is also, you can see all are actually from JEE mains paper of various years. So now this question is related to capacitor charging of capacitor. Okay, you can see the charge on a capacitor plate in a circuit as a function of time is shown in the figure below. Look here, the charge is, see, there is a capacitor which is actually suppose uh, connected to some battery or something like that, and it is getting charged somehow. So as the charge, this capacitor is getting charged, the charge on the capacitor is actually varying in this way with respect to time. Okay, so this is, so there is the curve you can see here. So initially 0 to 2 second it was uniformly increasing, then in between 2 to 4 seconds the charge become constant, and again after 6 seconds it is increasing further with a different slope. Okay, so you have to find out the value of the current at 4 seconds. T is equal to 4 seconds. That means at this particular point, what is the current flowing in the circuit? So what is the flowing? Actually, flow of circuit is, see, current means what? Time rate of change of charges. That means what? What? This means the slope of the curve. Here, this is QT. This is QT curve. So in that QT curve, you have to find out the slope. So what is the slope over here at 4? So this is the portion, right? At 4 seconds. Slope is actually, since it is parallel to time axis, so slope is 0 over here. Slope is 0. If the slope is 0, what it implies the current also 0. So the answer C will be the correct answer for this question. Okay, so dq dt is the current. You have to find out the slope of the qt curve, and at 4 second qt curve is like slope at qt this seconds is 0. So current will be 0 at 4 seconds. Now let us solve this problem. This is also related to capacitor. So actually I'm just picking up from JEE papers. So as it is coming, like I'm just taking the important problems which you may feel little bit of difficulties, or maybe those are little bit of tricky. So I'm taking this kind of problems. Actually, there are many problems. Will further go on with this discussion for at least 2 more classes, so that we can finish maximum important problems on this chapter. Anyway, so see here you look in the given circuit, you have to find out the charge on 4 coulomb. Let me tell you, uh, the process you have to solve here is actually you have to find out the equivalent circuit for this. First of all, equivalent circuit. Okay, so what will be the equivalent circuit? These are parallel combination. You have to make it. You have to find out the equivalent of that. So this will give you this, since they are parallel. So I can write 6 microfarad. So a single capacitor, and this is 4. So 4 and see this 4 microfarad and 6 microfarad. Now they are in series. You have to find out 1 by this is equal to 1 by 6 plus 1 by 4. So it will give you this much, and finally C equivalent will be 12 by 5. We'll just keep this as it is. So let me get the equivalent circuit for this. You might be thinking, why don't we just add this also? No, there is a purpose. We'll see that. So we have equivalent circuit now. And this is connected to 10-volt battery. Okay. This is my 3 microfarad, and this is 4 microfarad. Sorry, this is actually the equivalent one. 12 by 5 microfarad. Okay. This is, so you have to find out the charge on the capacitor. Actually, I would have not done this also. From here itself, we can just find out. See, one thing is very clear, that these two are actually parallel. So this branch, and this branch, they will have the same potential difference across them. See, so the potential drop across this is 10 volt, and this 3 microfarad also, across 3 microfarad also 10 volt. I don't even have to go here. I don't even have to do this. Okay, we can just directly do it. And one more thing you have to remember, in a parallel circuit, so the total charge will be actually divided, Q1 and Q2, like this. Okay, total charge will be divided into 2 branches. Okay, 2 branches. See, since this part and this part in series, the same charge Q2 will flow through both of them. Then it is very easy. So the charge on 4 microfarad will be Q4 microfarad is equal to 4 microfarad into the 10 volt. I hope you will be agreeing with me, because Q is equal to C into V, and why we have taken only 4, as you have the other this parallel combination of 5 and 1 microfarads also, because we know this Q2, which is flowing through the whole branch, will be the same. Like, see, this Q2 will be flowing through this also and this also, the combination of this. So that's why I'm just directly multiplying C into V to get the charge. So so this is 40, this will be actually 40 Okay, let me Q into, just a minute. Okay, so this is 4. What was that? 5 by 12. So this was 12 by 5 anyway. 12 by 5. Okay, we have to I think we have to go with this, because the whole charge is not only passing through this. That is the mistake I have done then here. Actually, okay, just a minute. Let me just redo it. Okay, let us go with the equivalent circuit. Here it is, equivalent capacitance we have found out, 12 by 5. Okay, and this is 3 microfarad. This is 10 volt. Okay, actually this is the capacitance microfarad. This, in these two branches, Q2 will be flowing. Okay, so this is Q1. Actually there was, okay, so not only this Q2 will go, as a combination Q2 will flow. So that will be the correct concept. Okay, so you have to then find out the equivalent of this branch, equivalent capacitance of this branch. So that is 12 by 5. Now it will be all right. So 12 by 5 into 10 will be microcoulomb. This will be microcoulomb. Okay, so 24 microcoulomb will be the correct answer. Okay, so I was actually a little bit confused about this thing. Okay, now I hope you are okay with this. Why we have to take the combination of these two or equivalent? Because as a whole, this combination will carry Q2 charge. Okay, and this 3 microfarad as a whole will take Q1 share. Okay, not only this 4 microfarad will take this Q2, but the whole branch. But anyway, since it is flowing through this, okay, flowing through both the component here, 4 microfarad and this combination, even if they are since they are in series, this Q2 will be same for this particular branch and this particular branch. Okay, so Q2 will be calculated in this way. So it is actually 24 microfarad. Now I think we are already done with the time. Next day we'll pick up few more problems. Today I'll finish it here itself. So thanks for your patience. I'll just conclude the class here. So next day we'll pick up few more problems like this and solve this problem also. Okay, okay then, bye for today.